So the first video compression algorithm that we are going to see is called as the H.261. So the topic is video compression, under which the first particular method or algorithm is called the H.261. All right. So this is actually originally invented for the video telephony over the ISDN types of lines. So in maybe in the networking or communication subject, you might have heard about the telephonic networks, right? And in case of the sorry, hello. It's one of the video compression standard, and this was originally invented for the what is called as the video telephony, and it's specific to one of the type of the network that is called as the ISDN lines. Right? So that's a kind of network present in the telephonic switching networks. So in that, if the video also wanted to be transformed, so you have something like a restriction on the total available bandwidth. Okay, so within that bandwidth, right, people wanted to transmit even video, means right, you have to perform a compression of the video, right? So originally it was invented for that purpose. Okay, later on, right, the H.261 was upgraded to 263, 264, and so on. So later on, as and when the technology changed, right, so they actually even changed the technology of the compression as well. Okay, right. So this particular standard is basically it describes the various components of a video conferencing system, and it also defines a narrow band multimedia, what is called as a terminal, for the compression technique. Okay, so this basically describes the uh, various components of a video conferencing system. That is one of its feature, because right, whenever you transmit a video, you should be able to receive the video as well. So overall, when multiple users do the same thing, right, it becomes a conferencing system. All right, so that's what is the fundamental idea behind this. All right, now this H.261 compression algorithm basically uses two different redundancies in an image sequence. All right, so what are the two different redundancies possible in case of a video? First one is called as a spatial redundancy, and the second component is called as a temporal redundancy, right? So normally whenever the H.261, right, initially it was introduced, right, people could observe whatever the compression ratio we got, right, it was huge, right, because at that time there was no other compression technique which could do this much of compression. Okay, but nowadays we have much advanced techniques, but for that time, I think this was around 1990s or something, right? So it was originally invented at that time. People thought that, okay, this is the biggest amount of compression that can happen, right? Why? Because the fundamental reason is that H.261 takes two types of redundancies into consideration whenever the compression is being performed. All right. So I'll write one point here. That is, this algorithm uses two types of redundancies. Two types of redundancies uh, in videos. Okay, what are the two types? The first type is called as a spatial. first one, and the second one is called as a temporal. So first one, the spatial is nothing but it considers the videos are made up of several images being played one after the other. Each image, if you consider, it is made up of several pixels. So the relationship between the pixels is the spatial, okay? And the temporal is you change video, you change these pictures one after the other, right? So with respect to time, something is varying, right? In that direction, if you look at it, it's called as a temporal. All right. Okay. So two things. One is in an image, that is a spatial. Within the image itself, something you observe, right? So that is a spatial. Yes. Temporal means as you move with the time, something changes. All right. So that's what is the case. Now, another. This is right now we are discussing about various characteristics. Okay. So we can consider that the next characteristic is that this H.261 also supports the very low resolution formats, right? Even if your resolution is very less, still it's going to work with the H.261 for compression purpose, because normally we have, as already we mentioned, there will be a bandwidth constraint because you have to send audio plus video, right, on a telephonic conversation lines, correct? So uh, like very good quality, if you expect, that may not be possible with this, because nowadays we have very good, we know what is it, what do you mean by very good quality, like 4K resolution, right, etc., right? But originally when it was developed, they didn't feel that issue at all because they had no high quality videos at all, right? Even the images which were being taken at that time were of nominal quality only. Okay, so the fundamental idea is that this works flawlessly in case of a low resolution image formats or low resolution video formats. Okay, so because there was a bandwidth constraint originally whenever it was developed, like you see the maximum, if you look at the value of the bandwidth that it usually supports is approximately 384 kbps. That's the maximum value of resolution supported, okay, right? Maximum bit rate. So you understand that, okay, in case of a 360 through 384 kbps speed, right, what would have been the resolution of the image or the video which you can receive, right? So it was low value, but for that time this was a bigger achievement. All right. Okay, so I'll write one point here. It supports low resolution. It's a low resolution format only, right? I cannot go for a very high resolution formats. This is due to the bandwidth constraints during the time of its invention. Okay, so we have two types of formats supported. The first format is called as the CIF format, right? CIF. This format is normally, right, whenever you use H.261, this is, I think this is sent in 300 and something. Okay, so this is 352 into 288 pixels, right? So that's the first thing. And there is another format. If you further want to reduce the bandwidth, right? You normally nowadays also we have these kind of techniques, right? That is called as a QCIF. So here the Q stands for the quarter of that value. So there is a CIF technique. So if you, I don't know whether you have come across this Q, the CIF stands for common intermediate format. Okay, it is one of the format in which you can save the images. All right. So CIF, if you were using for a H.261, then that actually supports 352 into 288 pixels. Whereas if you further want to go down and reduce the quality of your image, right, or the video, QCIF is also supported. So that will be 176 into 144 pixels, right? This is what was supported. Again, right, the maximum frames you can send was something around 30 fps, frame per second, right? Can be reduced anything lesser than that, but not exceeding 30 fps. All right, so I'll just write the frame rate supported would be, right, 30 fps. This is the max value. Maximum is that, anything lower than that will work. Okay, so this is what is the basic idea about this technique. Now we'll go to the basics of the H.261 directly. All right, so in H.261, what are the basic idea, right? You consider a frame of video as a screenshot of your data set. Like I have multiple frames coming up, right? Multiple images you can consider, right, in the video, right? So first you try to consider a frame of video, okay, as say a screenshot. We'll begin from there. Now we want to code this frame fundamentally. In the sense, you want to make some codes out of it so that code is in a compressed format and you can either save it or you can transmit it. All right. So that the codes used for these frames are of two types in case of H.261. Okay, so two types, two types of code frames are used. Okay, so the first one is called as, right, it's called as a I frame. Let's look at the iframe in short. Normally, the iframe basically stands for I for intra, I-N-T-R-A, intra frames or intra coded. Okay, C-O-D-E-D, intra coded frames. Now, as we know now, we are supposed to look spatially and the temporally, correct? So spatially, the spatial redundancies can be explored in this iframe. Okay, so this iframe is basically coded by you try to explore or do some research. I can write by exploring the redundancies, within uh, within a frame. Like you consider the image, right? Single image out of your video. Every image you look at the redundancies inside that, like pixel wise relationships, right? So just we can consider this to be right now I am considering a simple image. So what you do for image compression, that's what you are going to do here, such as JPEG coding. Right, JPEG coding does what? JPEG coding looks at a video, looks at a given image. I'm sorry. Okay, consider an image and looks at the redundancies present in that. Right, it's only image. Right. So if you are doing the image processing, there is no question of video. There are no multiple frames coming up. Only one frame is there. That itself is the image, and you try to compress that. That's what is happening in the iframe, right? So something like by doing this, we can say that we get some reference points of your video sequence so that you can concentrate. Maybe if you get the redundancies in a specific location of a picture, right, the next upcoming picture will also be of the same type, right? There may be very small movement present, right? Because if an object is moving in a video, when you look at the continuous stream of what you call pictures, right, you will see that object is going to move slowly, right, when you consider a frame to frame, right? So it means I have a redundancy in a particular picture, means there will be redundancy in the next picture also at the same position. So we call it like uh, reference point of the whole video sequence can be obtained by looking at the iframe. That's what is the significance. Okay, let me try to write that in one or two sentences. All right. So I wrote already. Okay, coded by exploring the redundancies within a frame. That's the first point we can write. Then we can write uh, this process is like performing the coding of an image compression, right? So example, we can write say JPEG or anything, any name you know, you can write it like that. It's a technique which wherein the compression happens only for a given single image. Okay, what is the use of this? Right, the use is that once you perform this, you will get the redundancies of a particular picture that implicates that whatever follows this particular image in the video, right, there might be redundancies in the same position. That means, right, uh, okay, I can write results results show the key reference key reference points. Okay, key reference points of the whole video. So for a complete video, this is what we can get whenever we consider the iframe. So how the iframes are encoded, we have a small algorithm or a flow chart for that. We'll write that later. Okay, so first type of frame is called as a iframe. Then we also, just now we mentioned that there is a second type of frame, right? For coding, the second type of frame is called as a P frame. Okay, so this is the P frames are basically it is intra. So previous one was intra. This is inter. Okay, intercoded frames. So in case of a P frame, we are trying to do the codings of frames that exploit their similarity with the previous frame. So we understood that once already we know that, okay, there is a redundancy in this location of a image. So the next image, whatever it comes in the form of in the video sequence, right? So there may be a specific location where you have a redundancy. So now you see that, look at your previous frame and decide what is going to happen now. So that's what will be done in the P frame. Okay, so P frame basically refers to the predicted frame, pseudo frame, etc. There are names like this. So I'll also write them here. So this is pseudo frame, or it's also some of the authors will call it by the name predicted. Okay, predicted frame. So when you see that, don't get confused. It's one and same. All right. So here, let me write that point first. Right. So these mm, codings of the frames exploit uh, the, I can write similarities. The similarities uh, with, say, the previously coded frame. Is it okay? Right. Now let's see the general representation of a H261 frame sequence. Right, I'll just write one example. Right, example of a H261 frame, say, sequence. So normally, let me try to write in this way. This is the time axis maybe. So there is a time axis. Varying with the time, I send different what do you call frames. Let's say, well, let us say we have uh, this as our H.261 frame. So first, maybe this could be a iframe. There is a specific format then in which we will send it. So IPPP, those are the pseudo frames. Then you have another I coming into picture. So normally these I's could be something like JPEG. Okay, I'll just write the coding used for I. All right, so this is JPEG. All right. Now this can vary. It's not a fixed number like three, right? In some cases, right, I followed by three P's, then one I, then two more P's, then one I, like that. It size can vary. All right. So, but the format is like I send a I followed by some number of P frames, then again I, once again P frames, that's all, etc. Right? Like this, we are trying to send. That's what we consider it to be the uh, H.261 fundamental type of encoding. All right. So iframe compresses the current what you call image. The P will just identifies what are the redundancies that are carried from the previous frame to this frame. All right, and it proceeds further in the same. Okay. Now, so let's look at the intra-frame coding technique first. Right. Okay. So intra-frame coding. Right. So they are considered to be the macro blocks for the coding. For example, macro block in a sense, you will consider a bigger area of pixels wherein you will try to explore the colors possible. All right. So what are the various colors that can exist over there? You try to explore that. All right. So let me write one point here. This actually includes the macro block coding. So what do you mean by a macro block, right? So a macro block is considered to be a range of pixels, right, of the order 16 into 16 pixels. So I can write 16 into 16 pixels wide. That is a span of the macro block. Now, the color scheme that is followed in case of this particular intra-frame coding is nothing but the just write a 16 into 16 wide span. That's the first thing, and it uses YCBCR, right? YCBCR color space. So there are various methods possible in which you can model a color, right? So the simplest one which we know is red, blue, and RGB, red, green, and blue, right? So RGB is one representation for a color. Any color you can try to represent using a red value, a green value, and a blue value. Correct. So I think you are aware of that. What are the other color spaces you have studied so far? If you are remembering, tell me. Otherwise, no problem. What are the other options using which you can represent a color is my question. Like first option is that okay, I give red value, green value, and a blue value. Okay, right. So RGB. If you specify RGB value, you get a color, right? Similarly, the R yes, similarly, RGB is not the only option you have. You have many other options. So if you have come across, you tell me. Otherwise, I'll tell you the answer. Okay. No? All right, no issue. So you see, maybe I think you are yet to study the image subject, image processing, image something related to image or pattern recognition. Uh, do you have any subject like that, which is image processing at least? No, no. No. OpenCV is a tool used for image processing. Okay. Huh. I don't know. There is a that's a programming part, correct? What you are saying is a programming part. Okay, so my question is, have you studied a theory subject called simple image processing? Yes. No. Okay, okay, all right. So then I should not ask that question. Okay, so actually, because maybe in the image processing side you will study this, right? So I'll quickly go about this. What is YCBCR, right? So first format is RGB. We know that what are RGB. I specify red value 102, green value 155, and blue value say 205. This means it is a specific color. You get a color, right? Color is represented by three coordinates, right? First one corresponding to red, then green, then blue. This is one type of format which we mostly are familiar with. We are not aware of other things. Either those who are interested in the photographical systems or video systems, right? So maybe a photographic experts or something, they normally don't prefer the RGB format, right? Even in our in our somewhat basic to moderate, not very basic, maybe the moderate camera systems will also have an option to shift your color space. Okay, you are capturing the same image, you are capturing everything as it is. Okay, no change in the image quality or something. But what happens is you don't try to write the value in the form of RGB. Okay, you will try to write the first or whatever the first value you write here, right? Maybe I try to convert the RGB into maybe the other format YCBCR. That will be right. It same number can be represented, same color can be represented using a different number. Okay, something like maybe I'll try to write this as 10.5. It's the same color, maybe. Okay, as of now I don't know which color is this. I'm trying to give an example. Okay, let us say it's a color, right, closer to the blue particular case, because blue is highest, right? So then green, blue and green mixed, a little bit of a red color. So it's that combination which we are talking about. So you get something like 7.8 and maybe 8.9, something like this. Let's say we assume. Let me say that this color format is Y CB CR. So Y value is this, CB is this, CR is this. So I'm converting the same color into a different color space, right? It is something like you have a point in the XYZ coordinate system and you convert that and you bring the same point into the cylindrical coordinate system, just like that. Okay, just a comparison. So I had a point XYZ, I'm converting that into a spherical coordinate system. You see, value will change. I still have the three coordinates, but their values are now changed. Correct? So this is what is happening now. You have a different color space allocated for this kind of representation. Now, what is this Y stand for? I'll just write this. Y is actually the luminance of the image. Okay, so we call it as a luma. It's a luma value. Okay, and the CB stand for, this is actually the chroma. It's a chroma value. Chrominance is the actual term, right? So it's a chroma value for blue, right? And CR is again a chroma. Oh, sorry, spelling mistake. It's again, all right. It's a chroma value R for the red. So now you see, it's not the similar representation like RGB. right? It is something different. Okay, so luminance, you understand the brightness, it relates to the brightness present in the image. Okay, and the chrominance value, in the sense how much color content you have with respect to the blue and with respect to red. This is what you try to represent. Okay, right? So maybe you will get a very clear idea if you go ahead and do little bit of search about the conversion between RGB to YCBCR, maybe uh, in some website. Okay, you'll get a clear cut. They'll draw the pictures here, right? So triangular something they will draw some space like this, and they'll show you, right? So how the color spaces are defined and how do you convert. It's pretty much similar to our conversion between the XYZ coordinates into R, theta and phi, right? It's that kind of conversion that you can see. All right, so since as of now we don't have to touch that, because I just want one sentence saying that we use YCBCR color space in case of a H.261. That's all. Okay. So this I need to remember that point, right? I'm not going to use the RGB space. We are going to use the YCBCR space. Okay. Right. Uh, that's the first thing. And let's say again, after this particular usage of a micro blocks in intra-frame coding of H.261, then after that it uses uniform quantization. So we understand that we have a the various types of blocks, micro macro blocks are being divided, in the sense you from the image you obtain the macro blocks. From the macro blocks you use RCBCY type of representation, right? Okay, I'll write another point here just before this. Let me add one more point here that makes things more clear. Okay, so let me push this down. This point will come later. Let me zoom. Okay, so let me write this. So what it performs, basically we considered 16 into 16 pixel area, right? In which you get 4 Y blocks, right? And 1 CB and 1 CR blocks are used. In the sense everything is converted into 4 blocks of Y, right? That indicates the luminance, and 1 block of CB, chrominance of blue, 1 block of CR. Okay, it's a step, that's all. As of now, since we have not gone in depth in the image processing, right, we may not be able to understand this, but since our intention is just to learn the basics or the steps followed in the H.261, if you just remember this, that is sufficient according to me. All right, so the representation goes in this way, right? If I want to write a say write one block diagram corresponding to that, the same thing which we have discussed now, I can try to write it in this way. So there is, okay, so this, the four, whatever 4 blocks we see here, this corresponds to the Y block. Okay, because we said that there are 4 Ys. Okay, then I'll use a different color, maybe one is C red and CB, so I'll write red color here. So this is CR, and I'll use a blue color for the other one. Oh, sorry. Okay, no blue selected. Okay, this is the CB. Okay, all together we are going to call this as a macro block of an image, right? Remember, every pixel is represented in the YCBCR format, not R. Right. So the first step, what happens here is we apply what is called as a discrete cosine transform, DCT. Okay, so this actually is a 8 cross 8. Okay, let me do slight modification. Let me put this DCT process inside a block itself, so that we can say that okay, this is how the steps are being taken, right? Instead of, so let me write in this way. So let me write this, and here I am applying the DCT. Okay, then we already have discussed that this is something like a DC Discrete cosine transform deals with the DC components present in that, not the variation. What is the constant value in each of the pixel? It deals with that. Okay. Again, right? You are processing in a 8 by 8 format. So at the output of the DCT, you still have the 8 cross 8 available. Okay. It's a size of the image, right? For each 8 cross 8 image, what you do, you apply another process. I think we discussed now. This is uniform quantization. It's a uniform quantization. So once that uniform quantization is done, right, you get the remaining, or I can write rest of the JPEG is what you get at the output. So remaining part will come at the output. So that can be used for your, you can save that or you can transmit that. This is the I frame coding part. So similar to this, we also have the second part that is called as the interframe or the P frame. Correct? So let's look at that now. So this is inter frame, interframe coding. Right. So the fundamental idea behind this frame coding is that you try to encode the difference between the previous frame and the current frame, right? The difference comes into picture just because of the motion of an object. Otherwise, everything remains same. If I'm trying to take a video of a still object, you see no difference between the current frame and the next frame because object is not moving, isn't it? I'm trying to, right, capture the video of an object which is stationary. So what's the difference, right? Irrespective of which particular image you are looking at in the given video sequence, right? We don't observe any difference because object is not moving, background is also still, everything looks the same, isn't it? But whenever one object moves in a given sequence of photos, or in a sequence of photos converted into video, whenever you look at the one frame and its next frame, only the object's position will change, background etc will still remain same, no change in the color etc. Correct, isn't it? So the basic idea behind the interframe coding is that here we are trying to encode only the difference, encode the difference of a motion compensated, a motion compensated part of, we call it as a target frame. Okay, target frame is the name of the particular frame which you are targeting. Okay, so this has to be done with respect to, with respect to a decoded reference frame. So you see, here we are supposed to consider one of the frame as a reference frame. We call it as a decoded reference frame. It's called as a decoded reference frame because you are very sure that this is where the object lies. Okay, in that particular frame, you are very sure that okay, this is where the object is identified, and because of that object being located at a given point in the image, you know the redundancies associated with them. All right, so that's the reason. Okay, so now let's look at the reference frame now. So the reference frame is actually which frame? Can you tell me? It should be the previous iframe only, right? Because in the iframe only you perform all the spatial redundancy analysis. Spatially, you look only in that. You may have the previous p frames, but the previous pre frame is actually not a reference frame because okay, I can try to make one small change in this diagram so that it can give you some more idea. All right, so the idea in the sense, let me say what you are trying to refer here. All right, so I'll try to put an arrow mark. So this p frame refers to the previous I frame. This also refers to the previous iframe. You see, you are not looking at the previous p frame. This also looks at the iframe as the reference. Okay, so I'll write the reference here. Is it okay? I hope that is clear. All right, so let me write that point here. Uh, the reference frames are the previous iframes. Okay, always they are the previous iframes. Okay, so we know that we are looking at the iframes, which are the previous iframes, and we are going to call them as the reference frames for the p frame part, isn't it? Okay, fine. Now, you see that there is a possibility of obtaining what is called as a the motion, right? Because the object might have moved in the second image. In the sense, when you look at the p frame, right, with respect to the I frame, the object must have been moved to a new location, isn't it? So what we do here, we call a motion vector, right? So inside this particular technique, right, after I identify the reference frame and I obtain the p frame corresponding to that, now what happens here, we try to obtain, or we first try to define a motion vector. So we'll write define a, it's a motion vector. So what do you mean by this motion vector? It actually talks about the offset with respect to the best match for this macro book. In the sense, you have a reference where the object was present in the reference. With respect to that, how much you have moved, right? For example, right, let me say the object was here, right? And when I, this is the I frame. Okay, let me say that I have a p frame now. In this p frame, you see this was the original position, and now it has moved to this. So you see that you can put a bounded box over here. So with respect to this, there is a arrow indicating in this direction, saying that the object is moved in that direction, right? So that is what is the motion vector. So let me write what is the motion vector now. It actually talks about the offset. This is the offset with with respect to the best match. Best match for the given macro book. I think we call it as a block, right? I'll call it as the same way. Okay, there are several names available in different references. Okay, so some calls it as macro block at macro book as well. So let me call it as a macro block because we already use the same book. Okay, so now let me try to write a diagram corresponding to the inter-frame coding. So here, by our understanding so far, we should know that there are two frames required. Okay, so let me write one frame and I'll copy that same thing to the other location. So let me consider an image of the following type. Okay, let's consider that there are 16 different pixels. Okay, and I understand that I need one reference for this particular macro book. So let's paste that over here. Okay. Now what happens here? You let's try to understand the requirement. Like okay, let me change the color and draw one object first. So let's say uh, there is an object located in this particular portion, right? This is the something like I'll call this as a target. Okay. In case of a reference, you can consider that to be the previous frame. All right. So in the previous frame, right, maybe the object is located at a different position from where it moved to reach this particular position, something like this. You see, now it's the same object, right, located in a different in the previous image it was here, now it has reached to the target position. So I can actually understand that from the previously located object I can actually draw something like, okay, this object is going to reach something like this position. All right, maybe very closely I can write. So you can see that I can actually try to mark a motion vector. All right, so could be the motion vector. Again, I'm drawing at random now, so could be you can draw something like some arrow mark here showing that will be the motion vector. So that's the motion vector which we were which we were talking earlier. Okay, right. So you see here, okay, let me give the names first, then we'll proceed with the diagram. So this is what I'm going to call the motion vector. That's the first thing. And here what we see, it's the macro block. All right. So what's the size? That should be a 16 into 16. Anyway, I have not written a 16 cross 16, but it should be understood now because H.261 uses a macro block of size to 16 into 16 standard. So here, this particular block is my reference block. Why it is a reference block? It is already processed. Okay, in this we know where is the object. Okay, now what you do? So this is actually we are processing the block by block. So from here I'll take a block. Let me directly draw the block over here. Say this is one block, right? And inside that given one block, let us say we have the object is detected, like maybe I'm looking for the red colored portion of an object. Let's say that's located in this way. So maybe I'm talking about this part of the diagram. Okay, right, I got something like this. Okay, and from the reference block also I'll get to know that, okay, this is going to reach to a particular region. So I'll just draw an arrow mark from here. Okay, so this block is what I'm considering here. Similarly, this block is what I'm going to consider here. Okay, there also I'm going to visualize a similar situation. Okay, it's the similar one. Whichever block that contains similar to this will be considered. Let's assume. Okay, there will be slight differences, but we are fine. We are okay with that. Okay, now uh, both of them will be brought into a block and you will take a summation. Okay, so let me write. So there is a plus. This block is connected. This block is also connected to that, and we calculate. So at the output, so one is positive, one is negative. So I get an error block. So we call it as MAE. It's a mean value of the error. All right. So that error will be considered. Now you take that and construct your YCBCR model. Okay, so with respect to the another frame, you are building this. That's all. So here also we are going to do the similar job of representing the YCBCR form. Okay, so it's a very similar process. So let me just create the YCBCR like the previous diagram. So this is a Y. This is okay. These four are for Y's, right? I'll write a Y here. this is completely say Y, then say this is the CR part, and this is the CV part. Okay, so this whole thing all together, right, is the YCBCR type of this. Now, once again, we apply the discrete cosine transform and the linear quantization. Also, you can perform the Huffman coding, etc. Right, so those are also supported over here. Right, at the end, you slightly modify your formats to get the output. Why the change in the format is required? It is because you have a change in the sense motion vector comes into picture, indicating that what is the direction in which the object is moving, right? So because of that, I need to do what is called as a motion vector compensation by using a step called as a formatting. Okay, I'll just write that so that the whole process is finished after that. Okay, so we have this. Now the output of this will be given to a DCT, discrete cosine transform. Okay, followed by this we perform what is called as the quantization. So once the quantization is also over, right, we perform what is called as a formatting. This formatting is required because it actually takes another input from the previous stage, that is the motion vector, in which direction object is moving, right? So this formatting provides you the final output, right? That can be sent as it is through the channel, or if you want to save it, you can use that as a P frame. Okay, so I frame and the P frames are the two constructional features of this H.261 particular way of video compression.